Good day, everyone. I hope we are all keeping safe. Today, we want to continue our topic in physics titled Refraction of Light Waves. In this study, we'll be seeing the definition and phenomenon of refraction of light waves, laws of refraction, refraction through rectangular glass block, real and apparent depth, then total internal reflection. What is refraction? Refraction simply means the bending of a wave the moment it gets to a new medium. Now it can cause change in the speed or the wavelength of the wave. Now from the diagram, consider a pen dropped inside a cup of water. You will discover the pen appears bent, but in the true sense the pencil is not bent. This is due to refraction. Now, considering the real diagram we are having, from P to O is what we call the incident ray, and it forms an angle with the normal called the angle of incidence. Also, the moment it gets to medium B, it refracts, forming an angle called angle of refraction. Now, phenomenon, when you consider a clear river or pond, it looks shallower. It's as a result of refraction. A rod or spoon appears bent or broken, just like the one I showed us earlier on. It's as a result of refraction. And also letter or print seen nearer when we place a thick glass block on them. All these are phenomenon that shows refraction exists. Then we go to laws of refraction. Now, laws of refraction, the incidence ray, the refracted ray, and the normal, the point of incidence, they all lie on the same plane. Let us go back to the diagram I showed us earlier on. This is the incident ray, this is the refraction ray, and this is the normal. All of them, they are all lying on the same plane. Now, going back to the laws of refraction, second law says the ratio of the sine of the angle of incidence to that of the angle of refraction is equal to a constant, and that constant is what we call the refractive index. And the refractive index by equation is given by refractive index n is equal to velocity of wave in medium 1 over velocity of wave in medium 2. Now, for light waves, we can say it is velocity of light in medium 1 over velocity of light in medium 2. Now, for water passing from a deep to shallow water, we say the refractive index is equal to the velocity in deep water over the velocity in shallow water. Refractive index is also given as the sine of the angle of incidence all over the sine of the angle of refraction. This particular equation is also called Snell's law, where R is the angle of incidence and R is the angle of refraction. Now we go to refraction through rectangular glass block. We want to consider how rays of light is being refracted when we use a glass block. Consider what we are having on the screen. A, B, C, and D is represented as a glass block. The moment we incident light through it, first of all, the moment the light passes from air into the glass, it is refracted. These are refractive angle. And also the light will also come out from the ray. That is what we call the emergence ray. The emergence ray and the angle of incidence will always be the same because it is from air to the glass and also out again to air. Now, because the glass is thicker or is more dense compared to that of air, our refracted ray will bend closer to the normal. So, but the moment it is coming out from the glass, it takes back the angle of the incident on which we incident the light as it enters through the block, and then it comes out with the same angle. Now, if you consider what we are having an air to glass medium, and here we can also put Snell's law by saying the sine of the angle in air all over the sine of the refracted ray inside the glass. All equation applies. Now we want to consider real and apparent depth. Just like we said, when you place a thick block, a thick glass block on top of a sheet of paper, having letters or print on it, you will discover the letters are kind of raised. That is what we call, that is a phenomenon of refraction. Now, the raised length from that glass block is what we call the apparent length, while the original thickness of the block is what we can consider as the real depth. Now, the real depth, the apparent depth, and the refractive index, they are related by the equation which is n equal to real depth all over apparent depth. Then we see total internal reflection. Total internal reflection is the reflection of an incident ray as the interface between the medium of incidence and another medium of lower refractive index when the angle of incidence in the denser medium exceeds the critical angle. Now, what is the critical angle? Is the angle of incidence in denser medium when the angle of refraction is less dense. In the less dense medium is 90 degrees. What we are having in the diagram, when we incident light through this glass medium, we will have a refractive ray at the end. But when we keep on increasing the angle of our incidence, it will get to a time our refractive ray will make 90 degrees with the normal. Now, the moment we keep on increasing the incident ray and it exceeds the critical angle on which it makes 90 degrees, then we will have an internal reflection instead of refraction. Now, from this last diagram, this angle, the rays of light didn't refract out of the glass block. Instead, it is reflected internally out. This is what we call total internal reflection. In nature, we see total internal reflection. Okay, for total internal reflection to occur, the following conditions must be met. Number one, light must be traveling from an optically more dense medium to an optically less dense medium. Number two, the angle of incidence in the denser medium must exceed the critical angle. And the critical angle and refractive index are related with the formula n equal to 1 all over sine c. Now, earlier on, as I started by saying, total internal reflection is seen in nature, in mirages and mirage, and also the wide view of fishes underwater. Now, let's consider the mirage. From what we are having on the diagram, mirage. Now, when you are traveling on the highway, when you look ahead, it will look as if there is pool of water ahead of you. On getting to the place where your vision assume the pool of water, it appears to be nothing, empty. What we are seeing is just a mirage. Now, what is happening there? Let's go to the diagram. Here we are having a palm tree. The observer seeing it is in the palm tree inverted, and a pool of water in between. Now, what is really happening? A cooler air is more dense than the hot air. Thus, as the observer looks at the palm tree on a hot sunny day, there is a kind of pool of water in between. But the moment the observer approaches this region where the pool of water is, we discover there is no pool of water at all. And at the end of the day, the palm tree appears inverted. Now, talking about the wide view of fishes underwater. Fishes underwater, they have the ability to cover a large field of view. It's as a result of total internal reflection. So, in nature, total internal reflection occurs in mirages and in the wide view of fishes. Now, let me drop a brain teaser. Now, let's consider light passing from air through a rectangular block of glass with parallel fixed 4.5 cm apart at an angle of incidence 52 degrees. Now, let us find the lateral displacement of the ray and the angle of refraction. Now, consider the brain teaser critically. We have a rectangular glass block, and we say with parallel fixed 4.5 meters apart. You know, when we talk about the block is supposed to have a thickness, and the thickness is 4.5 cm. Now, having an incident angle of 52 degrees, so you have to look for the lateral displacement of the ray and also the angle of reflection. Please ensure you try out the brain teaser, and when we meet again, we will solve the brain teaser together. Thank you and have a nice day.